I have kind of been a math nerd my whole life and used to do things like searching for patterns in prime numbers, solving Rubik's Cubes and stuff like that. And that's actually kind of how I got into neuroscience. So the problem that I'm working on right now is it's really inspired by a treatment for Parkinson's disease called deep brain stimulation. And that's interesting because a neurosurgeon, not me, but a neurosurgeon will implant an electrode into the patient's brain. It's called the basal ganglia region. It's kind of the motor control region. And that electrode is hooked up by a wire to a pacemaker implanted in their chest, and the pacemaker injects an electrical signal into the brain tissue. And it turns out that if you choose the right signal, then it can make the symptoms of Parkinson's disease go away, the tremors and so on. And it's almost like magic when they can turn on and off the pacemaker, which provides the stimulus. When it's turned on, the patient seems to be behaving completely normally. They can, do typical motor tasks that anybody can do. When they turn it off, suddenly the tremors come back almost instantly. And then they turn it back on and the tremors go away. And so it's not really well understood how this works, why it works, but it's clear that it does. What we're trying to do is to make it work better. So a hypothesis for what's happening with patients with Parkinson's disease is that the neurons in this particular brain region are too synchronized. They're pathologically synchronized. And why might that lead to tremors? Well, you could imagine every time one of these neurons fires a spike, it transmits a signal down to a muscle telling it to contract or not. Now, if it's only one neuron doing that, then it doesn't cross a threshold, nothing happens. But if a lot of neurons are spiking at the same time, then you get a signal which is strong enough telling a muscle to contract. And if this happens over and over, then you get a tremor. It keeps going. Now, how do we disrupt that synchrony? That's really kind of what we're thinking about when we design a new stimulus. One idea we had was to exploit something called chaos theory, which is an idea developed by physicists and mathematicians a few decades ago. The most famous example of chaos theory is something called the butterfly effect. And the idea here is, imagine that you have two parallel universes, so to speak, where in one universe there's a butterfly in Brazil that is just sitting there and doesn't flap its wings. And you wait 2 weeks later, you look at the weather in Texas and the weather's beautiful. Now in the parallel universe, suppose the same exact situation, everything's the same except now the butterfly flaps its wings when it didn't before. Now that can create a little eddy, which then interacts with other eddies and so on and can grow into something big. And ultimately, 2 weeks later, maybe there's a hurricane in Texas. So just this really small change, this small flapping of the wings, can lead to a very different outcome. That's something we call sensitive dependence on initial conditions. What does this have to do with deep brain stimulation in the brain? Well, if neurons are firing at the same time, you can imagine that they have very similar initial conditions. Now, if you can design your system to be chaotic in the sense that you have sensitive dependence on initial conditions, then the behavior of the neurons diverges, and it means that they desynchronize from each other. So we actually design stimuli in order to enhance that effect, in order to make the neurons move apart as quickly as possible in some appropriate space, which leads to the desynchronization and therefore the alleviation of the symptoms of Parkinson's.